I will start with a general introduction that will be maybe a bit lengthy, but I guess that not everybody is an expert in wave function theory and the precise problem of the basis set convergence. So after this introduction, I will go through the derivation of the theory and conclude with some numerical examples. So what is the main problem in quantum chemistry? Well, actually, I have the same equation to be solved since 1925, the good old Schrödinger equation. And the main problem, of course, is the interaction between electrons. Okay, so you have this sum of Coulomb pairwise potential, which creates the electronic correlation problem because the electrons, they just hate each other, so they don't want to be at the same place. And so this induces a very complex form for the wave functions. And so to deal with this complicated problem, we have in quantum chemistry, at least, essentially two methods. So wave function theory, which is systematically improvable but expensive, and density functional theory, which is cheap but not systematically improvable. So just in order everybody to rely on the same ground, I will just introduce wave function theory in a nutshell. So the first thing in wave function theory is the basis set. So we use a one particle basis set that I call here B, which is a set of hydrogen-like functions centered on atoms. So we have S function, P function, D functions, and this kind of stuff. And then from that one particle basis function, you build Slater determinants as a basis for your n-electron Hilbert space. So of course, a Slater determinant is just an antisymmetrized product of this one particle function. And then eventually your wave function in your basis is going to be expanded as a linear combination of these Slater determinants. And then with that ansatz for the wave function, you just try to solve the Schrödinger equations in your basis set. And if you take all the possible set of Slater determinants that you can generate with a certain number of electrons and a certain number of one particle basis function, you obtain what is called the full configuration interaction in the basis set, so the full CI in the basis set, which is the exact solution to the Schrödinger equation within a basis. Of course, this is nice as a target, but in practice, it's not feasible, or let's say it's feasible for few electron systems, because of course, the number of the Slater determinants scales essentially exponentially with the number of electrons and the number of single particle basis function. And this is why quantum chemistry essentially, so in quantum chemistry for essentially a few decades, there have been a lot of proposal of methods, of approximated methods, and there are a lot of wave functions, acronyms and methods. But just keep in mind that at the end of the day, they all try to approximate the full CI within a basis set. Okay. So now, what is the effect of the basis set on the wave function itself? To understand that, we first have to understand what are the exact conditions that we know in wave function theory, and that's essentially the electron cusp conditions that were derived essentially by Kato in '53. So we know that if you consider an exact wave function, psi, so by exact, we mean a wave function which exactly satisfies the Schrödinger equation, okay? And you Taylor expand it around R12 goes to 0, so around the small inter-electronic distance. So let's say for a two-electron system, you will find at 0 solar the wave function at R1 and R12 equal to 0. So essentially the probability that the two electrons are on top of each other at R1. So this is very system dependent, that's R1 dependent, okay? And then the first order term in the R12 expansion is 1/2 of R12, and this is really universal, which means that as it originates directly from the divergence of the 1/R12 operator, Coulomb interaction, which of course is universal, it is valid for any fermionic systems. Any Coulomb system with electrons, you always find this 1/2 of R12 as the first term in the linear expansion. So this means that this is valid for the helium atom, for a DNA branch, or for the uniform electron gas, which has nothing to do with the molecule. Okay. So now, if you do the same thing with an approximated wave function, so for instance, you take the full CI in a finite basis set, so incomplete basis set, what you find is systematically no cusp. So just in order to give a pictorial representation of that, which is very famous in quantum chemistry, but I'm not sure if it is that famous in other fields. Let's take the good old helium atom, because for this system, the exact wave function, the exact ground state wave function, can be numerically known. Okay, and as it is a two-electron system, looking at the wave function is essentially looking at the two-body density. Okay, and so it's a spherical system. So for instance, one can take two electrons on a circle like this, okay? And so here you are on the cutting of the wave function where you have an iso density. And so therefore the good variable is the theta angle between the two position vectors. And that's essentially the electron-electron distance, okay? So you can just plot the wave function as a function of theta, and this is what you obtain. So that's the exact wave function. So what you see here is that you have a depletion of the wave function when theta goes to 0, which means that you have a depletion of the wave function as the electrons get closer from one another. And that's precisely the electron correlation problem, because the electrons, they hate each other because you have the Coulomb repulsion. So therefore you have a depletion of the wave function. And then what you see here is that you have a cusp, which means that you have this linear behavior, this 1/2 of R12 behavior. Okay. So now let's do the same thing, but with an approximated wave function. So we take a full CI in a basis set, okay, B, and so we take, for instance, so the full CI in a double zeta basis set. Okay, so here, as we are using a full CI wave functions, the only approximation is the basis set. And what you see here is that at long range, so when the electrons are far away, it's okay-ish, but at short range, you are clearly overestimating the probability to find two electrons when they are close, which means that eventually you will overestimate the Coulomb repulsion between electrons. So this has an impact on the energy also. And here you find no cusp, so you have a flat and smooth wave functions. Of course, you can improve your basis set. So you go to triple zeta. So here, double zeta and triple zeta is just a, let's say, a hierarchy of basis set that we use in quantum chemistry. So that's essentially going higher and higher in angular momentum, essentially. So if you go to triple zeta, you improve your wave function. And if you go to quadruple zeta, you improve and you improve. And eventually you go to 6-tuple zeta, which is overkill for the two electron systems such as the helium atom. So you converge systematically, but what you see here is that you always overestimate the probability to find two electrons when they are close, and you have no cusp. So just to summarize this, what you see as an impact of the basis set in wave function theory is that you have a slow convergence of the two-body density near the vanishing inter-electronic distance, which means that essentially the short-range correlation effects are poorly described. But you might ask, okay, so that's the beauty essentially of the wave function, but this is not really something that we need, the wave function. We want to compute essentially energy differences. So here I will show the impact of the basis set approximation on the atomization energies. So it is just the energy difference between the molecule at equilibrium geometry and the sum of the and the sum of the atoms that compose this molecule. So here I report the error with respect to the complete basis set limit. So essentially the experimental values, if you want, okay, for this set of 56 small molecules, okay. So these are essentially organic molecules. So these are weakly correlated systems near equilibrium geometry. So in that case, the so-called CCSD bracket T, so the coupled cluster is singles and doubles and perturbative triples, what is called usually the golden standard of quantum chemistry. So this CCSD bracket T is the full CI in the basis, roughly speaking. Okay, so here the only approximation or the leading order approximation is not the approximation to the full CI, but really the basis set. And these are the errors that you see with respect to the complete basis set limit. So this is the mean absolute deviation, the maximum deviation, and the number of chemically accurate energy differences. So what we call in chemistry the chemical accuracy is typically 1 kcal per mole, and which is typically 1.4 milliatomic units. And this chemical accuracy region you see is this thin green line here. And what you see here is that, of course, by increasing the basis set, you reduce the error that you do on the atomization energy, but still you have to push your calculation to essentially a quintuple zeta basis set, and for such a system as H3OH, a CCSD bracket T quintuple zeta calculation is something like heavy, and eventually you see that on average you are at 1.28 kcal per mole, and you only have not even the half of these molecules which are in the chemically accurate regime. So this was just to show you that the basis set problem in wave function theory is actually quite severe problem, and to get a convergence with respect to the basis set is a headache, because of course the computational cost increase drastically when you increase the basis set. So this was for the wave function theory. Now let's look at another theory and how does it deal with the basis set: density functional theory. So first, roughly speaking, how does DFT work from a wave function perspective? So in DFT, essentially what you do is that you express the exact two-body density with only one body density ingredients. So if this is the exact two-body density, with the cusp and all this kind of stuff, so that's a complicated object, you say essentially that you have just an uncorrelated product of one body density and this exchange correlation Hall, which you are going essentially to parameterize with only the one body density object, so the density gradients, and this kind of thing. So this gives you essentially the electrostatic, so that's really system dependent, but this is quite universal. So just to give you an idea, when you do an LDA calculation, essentially what you do is that you import the exchange correlation Hall from the uniform electron gas. And why you can do that? Because precisely when you look close enough in R12, you are in the region of the electron cusp, and therefore you are in a universal regime. And therefore, it's okay to import short-range correlation effects from the UEG, because they are essentially the same if you look close enough in the small R12 regime. So therefore, you just need to import something that is pre-calculated on a model system like the UEG, and therefore you can have like a kind of free range, so to say, with respect to the short-range correlation problem. And the fact is that the density converge rapidly with the basis set, and as everything is parameterized with the density, eventually the DFT or the DFA, the density functional approximations, they converge really fast with respect to the basis set. Of course, the problem is that you have long-range correlation effects such as strong correlations or dispersion forces, and these are clearly less universal, and therefore this is why Kahn-Sham doesn't really manage to capture these kind of effects with the semi-local approximations that we have in DFT. So this is why some people have thought about a kind of generalization of Kahn-Sham DFT, which is the so-called range-separated DFT. So in that framework, what you do is that you essentially split the electron-electron interaction into a long range and a short range. So the long range part is essentially an F of mu R12 over R12, so that's a smooth function. And then you have the short range part, so the complementary part, such that the sum gives you, of course, the usual Coulomb interaction. Okay. And here, mu is what we call a range separation parameter, which essentially tunes your interaction. So it's essentially the range of this interaction, okay? And also it controls the value of the interaction when R12 goes to 0, which is finite and proportional to mu. So in the limit of mu goes to infinity, you're back to the usual 1 over R12 interaction, okay? And so this becomes the 1 over R12, and this vanishes essentially. So the idea of range-separated DFT is that the wave function now is going to deal with the long-range non-divergent interaction, okay? So because it deals with that, it has no divergence in the interaction, so therefore the wave function has no cusp, and therefore, as it has no cusp, it has a faster convergence with respect to the basis set. And this is really something nice from the wave function perspective. But on the other hand, DFT also deals with the complementary interaction, which is short range, and therefore, as it is more local, you are more in the universal regime, and therefore it is easier for DFT to capture good approximation for the complementary functionals, okay? So essentially, it's a win-win, so to say, because you have a better treatment of the non-universal long-range effects with the wave function part than with respect to the Concham DFT. And of course, you capture in a more easy way the short range part. But of course, you have some drawbacks because in practice, you still have self-interaction problems. And also, even if the theory per se is independent of mu, in practice, because you make approximation on the wave function and because you make approximation on the DFT part, it depends on this parameter mu, and therefore it can be a little bit tricky to have a theory that depends on the parameter, essentially. So just to summarize this maybe lengthy introduction, so what do we know from wave function is that the wave function in an incomplete basis set has no cusp, which means that you have short-range correlation effects which are missing from your model, essentially. But also we know that the cusp comes from the divergent interaction. So therefore, the fact that the wave function in a finite basis set has no cusp is essentially equivalent to say that if you project the Coulomb operator in an incomplete basis set, therefore, in a way or another, you remove the divergence of the 1 over R12 interaction. So said in other terms, you can think as the projection in a basis set either as removing the cusp or directly on the Hamiltonian itself as removing the divergence of the Coulomb operator. So therefore, this looks like range-separated DFT, which also deals with a non-divergent interaction. And so the idea is to capture, essentially to make a mapping of range-separated DFT with wave function in a basis set. And that's what we are going to do. So first, we are going to link the basis set incompleteness of wave function theory with density functional theory in a clean way. That's essentially what Julien has talked yesterday. And then we are going to deal with to make a mapping between wave function theory and range-separated DFT. And then once that will have these two clean stuff, we can use a special kind of range-separated DFT functionals to cure the basis set problem of wave function DFT. At least that's the hope. So let's begin by the core of the theory. So a nice formulation of DFT is the so-called Levy-Lieb formalization of DFT, where you know that the exact ground state energy can be obtained as a minimization over densities. And you minimize the universal Levy-Lieb functional plus the nuclei electron interaction energy, which is just the integral of the nuclear electron potential with the density, which is of course system dependent. And the Levy-Lieb universal functional is universal in the sense that it only depends on the density. And how is it obtained? It is obtained formally as you give him a density and then you minimize over all possible n-electron wave function that gives you that density, and you minimize essentially the positive part of the Hamiltonian. So here, psi are developed, of course, in a complete basis set, and this is why you get essentially the exact ground state energy. And here, the important point is that really F is universal, and that's why it's the holy grail of DFT, and that's what people are looking for maybe 30 years. So let's assume that we know this functional, okay? A good friend gives you that functional. But in practice, you're still going to compute calculations in a finite one-election basis set. So therefore, even if you knew F, so the Levy-Lieb functional, you would perform this calculation over a subset of density, which I call NB, which are representable in your basis set, okay? So if you call N0B the density that really minimizes this quantity, and that gives you E0B, okay? The problem is that N0, the true ground state energy, might not be representable in your basis set. And so therefore, you know that this quantity that we call E0B, that Julien introduced yesterday, is necessarily an upper bound to the true ground state energy, okay? But the idea is that the restriction here is only on the density, because in your Levy-Lieb functional, when you plug a density in your basis set, the wave functions, they don't care. They are still developed in a complete basis set limit. So they can have the cusp, they can have dispersion forces, anything you want. And so therefore, this is why the restriction on the density is much weaker than the restriction on the wave function in F. Said in other terms, the exact ground state density is well approximated by this N0B, or that E0 is well approximated by E0. That's the idea. So now we are going to decompose this Levy-Lieb functional evaluated as our density in a basis set. So instead of minimizing over all possible set of wave functions developed in a complete basis set, we are just going to use the wave functions that we have in your basis set. Okay, so we are putting here a restriction on this wave function, and therefore, for this to remain exact, you must have a complementary functional of the density, which takes what's outside the basis set for the wave function. And therefore, this E bar B is a complementary density functional, which is, of course, trivially expressed as the difference between the true Levy-Lieb functional and the one restricted in the basis set. And this must take, of course, into account the what is missing in your basis set. And once more, as the restriction here that we do on the wave function is much stronger than on the density, this must be a substantial contribution to the Levy-Lieb functional. And an important point is that this complementary functional is not universal at all, because it depends on the basis set. So you can hardly think of something less universal than the basis set, especially in quantum chemistry, where you have a few thousand of basis sets. So, said that, you can just rewrite everything and recompose, and you can just rewrite everything in terms of a minimization over wave functions. Okay, so you just minimize the expectation value of the Hamiltonian over these wave functions in your basis set, and then you have the complementary density functional that is evaluated at the basis set. So the wave function that minimizes this equation here, so it satisfies a self-consistent Schrödinger-like equation. So if you want, it's a kind of generalization of quantum DFT, in the sense that you have the usual Hamiltonian plus the derivative of the functional derivative with respect to the density of this complementary function. And so here, this is just a one electron effective potential that depends, of course, on the density of the solution, which is why in practice it makes it self-consistent. But eventually, so it's, yeah, I mean, we are used to nonlinear equations in any cases. And the thing is that because you have here this one body potential, the wave function that satisfies this Schrödinger equation in a basis set B is not the full CI wave function, because the full CI wave function would be if you have just the Hamiltonian here. Okay, so this is why this quantity corrects for the energy, but this quantity corrects also the wave function, and so therefore the properties, as we are going to see in a minute. So you could say, yes, but the self-consistent approximation is a bit a burden, and I expect that this potential is relatively small and doesn't really change globally the wave function. Okay, so therefore you can just say, I don't want to do this minimization. I will just approximate this wonderful wave function, this pi 0b in my basis set, just as the full CI density, or said in other terms, I assume that the minimizing density in my basis is the full CI density. And we know that the full CI density are not that bad. So therefore, we introduced a non-self-consistent approximation where you just evaluate the previous equation at the full CI wave function, and you obtain a very simple equation, which is that the exact ground state density essentially can be approximated by the full CI energy plus this complementary functional evaluated at the full CI density. So far so good. We have a very simple equation, but full CI is too expensive. Okay, so therefore we just make a generalization to approximated methods. So essentially, we are going to approximate the full CI energy by the energy of some method X, and then we are going to approximate the full CI density by a method Y that don't have to be different. The only thing is that they have to do the job. That's essentially the main thing. So here, the non-self-consistent approximation, here you only add a scalar, just an energy, okay? So you correct only the energy and not the wave function. Now, of course, the question is, how do we deal with this unknown, not universal complementary functional? But the key thing is that as what is missing in the basis set, it's short-range correlation effects. So therefore, we know that range-separated DFT does precisely that. And this is why we are going to make a link with range-separated DFT. So the cornerstone of this is the introduction of an effective interaction that represents the Coulomb interaction projected in a basis set. So this is the corner. It is very important in the theory, but it's quite technical. So I chose not to put it in the core of the presentation. If you want, we can discuss about that later. But essentially, it really represents what is the action of an incomplete basis set on the Coulomb interaction. So this is a function from R6 to R that is essentially non-isotropic, non-translational invariant. And why? Because the basis sets are not translation invariant or isotropic. And this is why, of course, the fact that you project the Coulomb interaction in that basis, it kind of kills the beauty of the isotropicity and the translational invariance. But this function that we introduced is non-divergent when the basis set is incomplete, just as the interaction in range-separated DFT. And this comes naturally in the derivation. And most importantly, it has the correct complete basis set limit, which means that you can demonstrate that in the limit of a complete basis set, this weird function goes to the usual 1 over R12 isotropic and translational invariant interaction. And so therefore, what we did is to say, okay, we have this weird interaction that represents essentially our interaction in the basis set, but it's a complicated object. So therefore, we are going to fit this weird interaction with the long-range interaction that we use in range-separated DFT. So we are going to require that at coalescence point, so when R12 goes to 0, for each point R1, we want that this weird interaction coincides with the long-range interaction, which is essentially the interaction at coalescence point. But the problem is that here you don't have an R1 dependence, and here you have an R1 dependence. So the only way to do it is just to make this range separation parameter mu depends on R1. And if you invert that equation, you obtain just that the range separation parameter is essentially proportional to the weird interaction in the basis set at coalescence in R1, okay? So here we have a range separation parameter that essentially represents locally the incompleteness of your basis set that you are using, okay? And because we did things in a good way, because this interaction goes to 1 over R12 at the CBS limit, and that mu is the value at coalescence point, you can easily convince yourself that this range separation parameter goes to infinity when the basis set is complete, and therefore we know how does it behave. So let me give you a pictorial example in the case of the helium atom. So here I have represented the value of mu in R, so as a function of the distance to the nucleus of the helium atom for different basis sets. So you see that none of them are clearly isotropic or invariant, okay? And what you see is that in a double zeta, you have something relatively flat. And when you increase the basis set, the overall value of mu increases, okay? And you see that this increase is much more drastic when you're close to the nuclei. But this is somehow intuitive because the basis set are centered on the atoms. So therefore, they are you represent the correlation effects much better when you're close to the atom with respect to when you're at 2 angstrom, for instance. Okay, and so this is clearly an illustration of the non-translational invariance of the basis set. Okay, and you know that eventually, in the limit of a complete basis set, you will have mu that goes to infinity in every point in space, and that's the good limit. And so now what we do in practice is that we just use range-separated DFT functional to correct for that. Actually, we don't use the usual correlation functional. We use the correlation functional with a multideterminantal reference. So it's a special kind of functional that was introduced in range-separated DFT. And the idea is that we want to correct for the full CI. And the full CI is already correlated. And so therefore, we want a correlation functional that takes that into account. And that's the so-called multideterminantal reference correlation functional. But eventually, it's a functional that depends on the density, okay, just as the usual functional. And that now depends on this range separation parameter mu because you're doing range separated DFT. And so the idea is just that, there are different flavors of these functionals. I will not enter into details, but the idea now is just that we are going to use these functionals, but just the range separation parameter will be the range separation parameter of the basis set. And this is so something very simple. We approximate the complementary functional for a given basis and a given density in the basis as just these functional evaluated with a given basis and the range separation parameter of the basis. So now if we look from the computational point of view, it is very cheap compared to the DFT part to the wave function part, because this is just an R3 integration of a function. So you can use the usual DFT grids. You only need essentially the one body density, and the only part is to compute mu b, and I will spare you the math, but if you want, we can discuss about that. You only need Hartree-Fock quantity. So okay, so far so good. We have this way to correct for the energy. You take the energy of wave function x and you correct with the density of method y. Okay, so it is a simple DFT correction. It has the complete basis set limit, which is correct. And you can reuse pre-existing DFT methodology. And once more, it is cheap compared to the wave function. So now just a few results, and I'll be done. So these are the atomization energies I just shown you before. So that's the slow convergence of wave function theory. So now, just on top of these energies, we just compute our basis set correction, okay, with Hartree-Fock density. So very cheap thing to obtain. And this is what we obtained, actually. So this was the green line, okay, so the chemically accurate regime. We are essentially right on it from the triple zeta basis set. So just to give you now the numbers, these were the numbers with the bare wave function method, okay? And now if we just add this simple quantity here, which is essentially free compared to the CCSD bracket T, this is what we obtain. So we go from 14 kcal to essentially 2 kcal, and in double zeta, and within the triple zeta, we are already performing better than the quintuple zeta quality, and it keeps on getting better. Why? Because essentially we design everything such that it vanishes when the base set is complete. Now we have been able to correct for the energy, that's good, but we also want to improve the quality of the wave function, because this can be often expressed as expectation value over the wave function. So if I just take the dipole moment of a simple molecule, so BH, this is just an expectation value over a given wave function in my basis of the Z operator. And of course, so it depends on the quality of the wave function. So here I represent as a function of the basis, the convergence of this dipole moment as, so in CIPC, that's essentially full CI. I don't enter into the details. And that's the CBS, complete basis set. And you see that you have this slow convergence. And this slow convergence is, of course, due to the poor quality of the wave function because of the short range correlation problem. So therefore, what we did is is we say, okay, let's now try this self-consistent approximation. So as we know E bar B from unseparated DFT, we can completely compute the functional derivative, just as in Conchem, you know the XC functional, so therefore you can compute the functional derivative. So we solve this Schrödinger equation for essentially the same type of wave function, so the CPC, and this is what we obtain. So clearly, you see that just by changing the potential, so by changing the CI coefficients in your wave function, you obtain something that converges much faster, and that is way more stable. So this leaves me with the conclusion, essentially. So as I shown you, so essentially all the ideas are in this 2018 paper. So what I have present is that we have a proper theory to combine wave function theory and DFT. The cornerstone is that if you don't have a cusp in the wave function, it means that in a way or another, you're using a non-divergent interaction. It is systematically inferable and cheap, and you have the correct limits when the base set is complete. And it is actually competitive with the so-called explicitly correlated methods, which are the usual stuff that we do in wave function to cure for the base set problem, but which require much more machinery. So things that we also worked on, so we did more benchmarks on more systems, including transition metals, and it works also. We also introduced new functional for strong correlation. We are now computing properties as energy derivatives, so without the self-consistent procedure. And now we are also working on response theory for excited states. And also we are thinking on how to treat large systems, so with like 100 of atoms. And so with that, I would like to thank Julien Toulouse, who is my main collaborator on this project, Diata, who is in PhD with us, and Barthélémy also, who has worked as a postdoc, and my other collaborators on this project, and of course you for your kind attention. That will be all. Thank you.